The oldest light in the universe holds secrets we are just beginning to read. This faint glow, the cosmic microwave background, is a snapshot of the infant cosmos, but it is not a simple picture. Its light carries a hidden property called polarization, a subtle directional twist imprinted by the universe's very first moments. By the end of this exploration, you will understand 25 profound mysteries etched into this ancient light that defy our standard story of the Big Bang. Why does this primordial map seem to point in a preferred direction, as if the universe has a hidden axis? What could create vast, cold deserts in this first light that nothing seems to explain? We are about to journey through the data that cosmologists stare at, puzzles that whisper of physics beyond our textbooks. What does it feel like to look at a map of creation and see something that should not be there? That first great mystery is known, with a hint of scientific drama, as the axis of evil. The name itself tells you how unsettling this finding is to our understanding of the cosmos. According to the bedrock principle of modern cosmology, the universe should be isotropic. That is a fancy word meaning it should look the same in every direction, with no special place and no preferred axis. It is the assumption that the cosmos is fundamentally fair and even. Yet when scientists created their exquisitely detailed map of the cosmic microwave background, they found a ghostly pattern. The hot and cold spots, those tiny wrinkles in the fabric of space, are not scattered randomly like confetti. Instead, they show a faint but statistically significant alignment along a particular line across the sky, a kind of cosmic equator. It is as if you laid out a map of the Earth and found that all the mountain ranges, subtly but undeniably, lined up along one single line of longitude. This should not happen. The universe is not supposed to have a "this way up" label. What makes the axis of evil so much more than a curious oddity is that this same preferred direction, this same troubling axis, also appears imprinted in the polarization of that ancient light. It is not a fluke in one type of measurement. It is a signature written twice, in both the temperature and the directional twist of the oldest light we can see. The statistical significance is the key. In simpler terms, the chance that this alignment is just random noise, just a lucky coincidence in the data, is incredibly small. Think of rolling a die and getting a 6 20 times in a row. You would start to suspect the die was loaded. Cosmologists are looking at the universe's first roll of the dice and seeing a similar, profound unlikelihood. This is why it is so troubling. The axis of evil is not just a puzzle, it is a direct challenge. If the universe at its largest scales shows a preferred direction, then our most basic assumption about its structure, the cosmological principle, might be incomplete or even wrong. We are left staring at a map of creation that seems to point a finger in one specific direction, whispering that we have missed something fundamental about the shape and story of everything. This ghostly axis is not the only anomaly staring back at us from the map. There is a place on that ancient sky that feels, for lack of a better word, empty. It is a vast, cold desert in the first light, a region astronomers call, simply, the cold spot. In the cosmic microwave background, temperature variations are tiny, mere millionths of a degree. But this spot is different. It is significantly colder and much larger than our models of random fluctuations can easily explain. It is as if you were examining a detailed thermal map of the Earth's surface and found a single, continent-sized patch of land that was inexplicably, profoundly colder than everything around it. The first instinct was to look for a culprit in the foreground, something between us and that primordial light. The leading candidate is a supervoid, an immense bubble of relatively empty space in the constellation Eridanus. If such a vast nothingness existed along our line of sight, the theory of integrated Sachs-Wolf effect suggests that light from the cosmic microwave background passing through it would lose a tiny bit of energy, making that region appear colder. But here is the puzzle. The suspected supervoid, while huge, does not seem nearly large enough or empty enough to account for the profound cold we observe. The numbers simply do not add up. The cold spot remains stubbornly too cold. This is where polarization adds another layer of mystery. The patterns of polarized light around the cold spot show their own peculiar signatures. Some researchers have proposed that these patterns could be the fossil imprint of a cosmic texture, a hypothetical defect in the fabric of spacetime from the universe's violent birth, a kind of cosmic knot that left a permanent scar on the light. Others look at the polarization and wonder if it hints at something even stranger, a chance intersection with another universe in the multiverse, a notion that borders on science fiction but is taken seriously in cosmological circles. The true challenge is linkage. We have a profound effect, the cold spot. We have a potential cause, the Eridanus supervoid, but connecting them with our current physics feels like trying to fit a square peg into a round hole. The implication for our story of cosmic inflation, that period of unimaginable expansion just after the Big Bang, is significant. Inflation predicts a certain statistical randomness in the distribution of hot and cold spots. A feature this extreme, this statistically unlikely, is a red flag. It suggests that either inflation operated in a more complex way than we think, seeding these rare giant fluctuations, or that something else entirely happened in those first moments to carve this great cold mark onto the face of creation. These alignments become even more bizarre when we look at the next layer of the universe's geometry. Beyond the axis of evil and the cold spot, cosmologists have found a strange conspiracy between the very largest patterns in the ancient light. To understand this, you have to think of the cosmic microwave background map not as a simple picture, but as a complex musical chord. Scientists break this chord down into its individual notes, called multipoles. The lowest notes, the deepest rumbles in this cosmic symphony, represent the biggest possible structures on the sky. The first real note, after the constant hum, is the dipole, caused by our motion through space. The next note is the quadrupole, representing patterns that divide the sky into 4 large sections, like a 4-panel window. The note after that is the octupole, dividing the sky into 8. According to our standard story, these huge, fundamental notes should be completely independent. The universe's first moments should have created them with random orientations, like someone tossing a handful of confetti where each piece lands facing a random direction. Yet the data tells a different story. The quadrupole and the octupole, these 2 deepest fundamental notes of creation, are not random. Their hot and cold patterns are aligned with each other. Their axes point in similar directions. This is already deeply strange, a statistical unlikeness that makes cosmologists recheck their calculations, but the strangeness does not end there. This shared alignment, this cosmic conspiracy between the 2 largest scales, also appears to be curiously linked to our own backyard. The plane of this alignment shows a suspicious relationship with the plane of our solar system, the ecliptic. The chance that this double alignment, first between the 2 multipoles and then with our local geometry, is a random accident is vanishingly small. We are talking about odds so long they force a serious question. Are we seeing a fingerprint of physics from before the epoch of inflation, a fossil of a universe that had a preferred structure before it blew up. Or, more troublingly, is this a sign that we have not fully cleaned our window, the alignment with the ecliptic whispers of a potential foreground contamination, something from within our own solar system or local galaxy imprinting itself on the primordial signal? Yet years of intense scrutiny have failed to find a local source strong enough to explain it. This leaves the profound possibility that the universe's largest patterns remember a direction from a time before time as we know it, a direction that, by a coincidence that strains belief, happens to line up with our tiny planetary neighborhood. It is a mystery that sits at the precipice of discovery, asking if the flaw is in the cosmos or in our own point of view. The universe's first whispers seem to fall silent across the grandest scales. When scientists measure how the temperature and polarization patterns in the cosmic microwave background relate to each other across the sky, they find a profound and unexpected quiet. At angles larger than 60 degrees, which on the sky is a truly vast separation, the expected correlations simply vanish. It is a missing signal, a strange hush where our models predict a clear and distinct conversation. Think of it like listening to the echoes in a colossal cathedral. You expect a certain reverberation, a specific pattern of sound bouncing between distant walls. But in this cosmic cathedral, when you stand at one end and shout, the echo from the far wall never comes back. The space feels too large, or the walls are shaped in a way we do not understand. This lack of large-angle correlation is a direct challenge to the standard story of cosmic inflation. That theory of the universe's explosive initial growth predicts a specific spectrum of these correlations, a mathematical fingerprint that should be visible at all scales, including the very largest. The data shows that fingerprint is incomplete. The biggest patterns in creation are not talking to each other the way they should. One compelling line of investigation asks if this is a clue to the shape of space itself, a hint about cosmic topology. Could the universe be finite but wrapped in on itself in a complex way, like a video game screen where if you travel far enough in one direction, you loop back to the start? If the universe's fundamental size is smaller than the distance light has traveled since the cosmic microwave background was emitted, then the largest possible correlations we could see would be cut off, creating exactly this kind of deficit. It is as if we are inside a room whose walls are closer than we thought, limiting the longest wavelengths of sound that can exist here. Yet, so far, searches for a specific repeating pattern that would be the signature of such a wrapped geometry have come up empty. This pushes cosmologists toward an even more radical possibility. Perhaps the missing correlation is not an artifact of the universe's shape, but of its birth. Maybe inflation did not happen in the simple, smooth way we presume. It could have been a more chaotic, stuttering process, or it may have started later than we think, failing to imprint its signature on the very largest scales. Some theories even suggest the universe was not born from a singular point, but from a prior state we cannot yet describe, a state that left this specific silence in its wake. The quiet at the largest angles is not an absence of data, it is a positive signal of something missing, a cosmic blank space that is, in its own way, shouting for our attention. But the quiet at the largest scales is not the only whisper from the early universe that seems to defy our expectations. To uncover the next mystery, we must look closer at the specific twist of that ancient light, at a pattern so subtle it represents one of cosmology's greatest quests. This is the hunt for B-mode polarization. think of the polarization of the cosmic microwave background as a field of tiny arrows, each pointing in a specific direction on the sky. Most of these patterns can be created by simple, swirling motions of matter in the infant cosmos. These are called E-modes, but there is another, far more elusive pattern, a curl, like the fingerprint of a gentle whirlpool imprinted directly onto spacetime itself. This is the B-mode. Finding a primordial B-mode signal would be the smoking gun for gravitational waves generated during cosmic inflation, the ripples in the very fabric of reality from the universe's first violent fraction of a second. It would be a direct window into physics at energies 1 trillion times greater than anything our particle colliders can reach. The search for this signal is monumental, but within the tentative data we have, another puzzle has emerged. There are hints, and they are only hints, of an asymmetry in these B-modes. The data suggests the curl patterns that spin one way, say left-handed, might be different in strength or number from the curl patterns that spin the other way, right-handed. This is not a small detail. It points to a potential violation of parity symmetry in the laws of the early universe. Parity is a fundamental principle in physics that, in simple terms, says the laws of nature should not care about left or right. If you watch a physics experiment in a mirror, the mirrored version should also be possible in the real world. This symmetry holds incredibly well for the forces we experience every day. But if the primordial B-modes show a handedness, a preference for left over right or right over left imprinted at the birth of the cosmos, it would mean that the most fundamental laws during inflation were chiral. They distinguished between left and right. The implications are staggering. Such a discovery would provide a crucial clue to one of the great mysteries in physics today: the overwhelming dominance of matter over antimatter in our universe. The processes that could create such a parity violation are deeply tied to theories that explain why we are here at all, why the universe is made of something rather than nothing. It suggests that the seed for our entire material existence might be written in the curl of that first light, yet the evidence remains tantalizingly out of reach, buried in noise and foreground interference. The hunt continues, with ever more sensitive telescopes scanning the skies, because confirming this asymmetry would not just add a new chapter to cosmology. It would rewrite the book on how we understand symmetry and creation at the most fundamental level. The search for a hidden handedness in the cosmos leads us to a map that seems lopsided. The universe's first light should be a symphony of perfectly random fluctuations, a uniform crackle of static from the dawn of time. But when cosmologists measure the power of those fluctuations, the volume of that ancient static, they find a baffling imbalance. One half of the sky, a vast hemisphere centered roughly in the direction of the constellation Virgo, plays the music of creation just a little bit louder than the other. This is the hemispherical power asymmetry. It is as if you were listening to a recording of a concert hall and realized all the violins on the left side of the stage were consistently, subtly louder than those on the right, across the entire performance. The effect is small, only about 10%, but its statistical significance is robust. It appears not just in the temperature map, but also in the E-mode polarization, confirming it is a real feature imprinted on the infant cosmos, not an artifact of our measurement. Scientists call this a dipole modulation, meaning the strength of the fluctuations has a preferred direction, a gradient across the sky. This directly challenges the principle of statistical isotropy, the idea that the universe, on average, should have no special direction. We already have the axis of evil suggesting an alignment, and now we have this asymmetry telling us one side of the universe, was fundamentally more active, more potent, at the moment of its birth. How could such a thing happen? If the entire observable universe was once a tiny, subatomic region that inflated uniformly, how did one half end up with more primordial oomph than the other? One radical theory points to super-horizon perturbations. During inflation, space expanded faster than light, meaning regions of the universe were pushed beyond each other's cosmic horizons, unable to communicate or smooth out their differences. It is possible our entire observable cosmos is just a patch within a vastly larger, inhomogeneous whole. We might be living in a region that, by sheer cosmic luck, had slightly stronger initial quantum fluctuations than the region next door. Our sky would then show this gradient, this slope from a higher energy zone to a lower energy one. Another mind-bending possibility involves the shape of space itself. Could the universe have a non-trivial topology, a complex geometry that makes one direction fundamentally different from another? If the cosmos is finite and shaped like a vast, twisted cylinder or a torus, the way light travels and wraps around could create the illusion of a power asymmetry from our particular vantage point. We would be seeing the same basic pattern from different angles, making one hemisphere appear stronger. Yet, like the large angle correlations, searches for the telltale repeating patterns of such a topology have not found clear evidence. This asymmetry forces a humbling perspective. The cosmological principle, the bedrock of modern cosmology, asks us to believe we are not in a special place. But the hemispherical power asymmetry whispers that perhaps, in a way we do not yet understand, we are. Our entire observable universe might be tilted, just a local slope on an infinite and varied landscape of creation whose full structure remains hidden from view. The lopsided universe is not the only surprise hidden in the fine details of the map. As our telescopes achieve ever sharper vision, they reveal pinpricks of mystery scattered across the ancient sky. These are point source anomalies, tiny, intense spots of polarization with no clear identity. In the high-resolution maps of the cosmic microwave background, scientists expect to see the smooth, diffuse glow of primordial light, punctuated by the known foreground objects of the later universe, like distant galaxies or brilliant quasars. But some of these bright, point-like sources of polarized light refuse to match any catalog. They are cosmic strangers, unexplained sparks in the oldest light we can see. Imagine scanning a vast, foggy landscape at dawn, expecting to see only the soft, uniform glow. Instead, you spot a handful of impossibly bright, sharp lanterns shining through the mist, with no one holding them and no house nearby to explain their presence. That is the unsettling nature of these anomalies. Their polarization is strong and specific, meaning the light waves are vibrating in a distinct, coordinated direction, unlike the random scatter of simple heat. What could possibly create such a focused, powerful signal imprinted on this backdrop? The suspects are as fascinating as they are speculative. One candidate is a class of hypothetical exotic objects, like primordial black holes from the universe's first moments or dense knots of dark matter that could interact with light in unusual ways. Another, more dramatic possibility is cosmic strings. These are not strings in the everyday sense, but theoretical defects in space-time itself, infinitely thin cracks in reality left over from the phase transitions of the early universe. A cosmic string, with its immense density, could act as a gravitational lens, warping and polarizing the light from the cosmic microwave background behind it, creating a sharp, linear signature that might appear as a point-like anomaly in our maps. Then there is the more mundane, but crucial, possibility of instrumental artifacts. Could these be glitches, noise, or subtle calibration errors in the incredibly sensitive detectors? Teams have chased this down relentlessly, and while some point sources have been identified and removed, a stubborn few remain unaccounted for, persisting across different observational campaigns. This is why they matter so profoundly. The holy grail of this field is the detection of primordial B-mode polarization, the curl from gravitational waves. That signal is incredibly faint, a whisper buried under a roar of foreground noise. These unidentified point sources are like someone shouting in the library just as you're trying to hear that whisper. They contaminate the data, adding a layer of confusing polarization that must be meticulously identified and subtracted. If we cannot explain what these point sources are, we can never be fully confident that what we filtered out isn't, itself, a part of the primordial signal we seek. Their very existence is a reminder that our map of the dawn of time is still incomplete, littered with unexplained signatures that could be mere dust on the lens, or could be the first hints of physics existing only in our theories. These unexplained sparks in the ancient light force us to look outward, to consider how the entire cosmos might be moving as one. A deeper mystery flows from the cosmic microwave background, one that suggests a vast, invisible current tugging at everything we can see. This is the enigma of the dark flow. By studying the faint shadows galaxy clusters cast on the primordial light, astronomers claim to have detected a startling, coherent motion, a bulk flow of thousands of clusters all streaming in the same direction, as if pulled by a gravitational hand we cannot see. The key to this measurement lies in a subtle imprint on the cosmic microwave background called the kinetic Sunyaev-Zeldovich effect. As hot gas within these massive galaxy clusters moves through space, the electrons in that gas scatter the photons of the ancient background light. This interaction creates a specific, minute distortion in both the temperature and, crucially, the polarization of that light. It is like watching the wind. You cannot see the air itself, but you can see its effect on the landscape, the way it bends the grass in a field. By meticulously mapping these distortions across the sky, scientists can reconstruct the velocity of these galaxy clusters, not just their apparent motion from the expansion of the universe, but their peculiar motion through space. The controversial results suggest these clusters are not drifting randomly. Instead, they seem to share a common velocity, all moving toward a point in the sky near the constellations Centaurus and Vela, at speeds far greater than our standard models of cosmic structure can explain. This proposed dark flow is not a small ripple. It is a tidal wave of motion on a scale of billions of light-years, a coordinated drift that defies the gravitational pull of all the known matter in our observable universe. The implication is staggering. It hints that something immense, something with gravitational influence beyond the edge of what we can see, is exerting a pull on our entire local cosmos. This could be evidence of a superstructure from a time before inflation, or the gravitational tug of another, separate universe in a vast multiverse, a notion that pushes the boundaries of cosmology. Yet the controversy is fierce. Skeptics argue this signal is not a true bulk flow, but a systematic error, a collection of subtle biases in the data, or an incomplete understanding of foreground emissions from our own galaxy. They point to other studies that have failed to find the same strong, coherent signal. The polarization data from the cosmic microwave background is now the critical new frontier in this debate. Because polarization gives a cleaner, more direct measure of the kinetic Sunyaev-Zeldovich effect, it offers a chance to cut through the noise and confirm or refute the dark flow once and for all. Is this a real current in the ocean of spacetime, pointing to shores beyond our horizon? Or is it a mirage, a trick of the light as we stare into the deepest past? The answer would tell us if our universe is truly an island, or just one piece in an infinite, unseen archipelago. These strange currents and asymmetries force us to examine the very conversation between different aspects of the first light. The temperature map and the polarization map are not separate stories. They are deeply intertwined, and their relationship holds another layer of coded information from the dawn of time. This relationship is measured by scientists as the TE correlation, a precise statistical handshake between the temperature, T, and the E-mode polarization, E, across the sky. In the standard model of cosmology, this handshake should follow a very specific pattern, a predictable rhythm set by the physics of the early universe's plasma. But in several specific bands of this cosmic rhythm, the handshake falters. The observed correlation is either stronger or weaker than our theories predict. Think of it like listening to a perfectly composed piece of music, only to find that in certain measures, the harmony between the melody and the bass line is subtly but undeniably off. It is not a catastrophic error, but a persistent, nagging dissonance. This TE correlation is not just a random statistic. It is a direct probe of what cosmologists call the damping tail, the era when the universe was a seething fog of electrons and protons, just before it became transparent. The correlation tells us about the precise balance of forces during those final moments of scattering, about the density of matter and the behavior of radiation. When the observed correlation deviates from the prediction, it is as if a key witness to the universe's birth is giving testimony that contradicts the official story. The anomalies appear at specific multipole ranges, which correspond to specific angular scales on the sky. Some of the most discussed discrepancies occur around the multipole moment of 200, which represents structures of about 1 degree across. At these scales, the TE correlation seems to be suppressed. It is weaker than expected. This is profoundly hard to explain because the physics governing this era is considered some of the most solid, bedrock physics in all of cosmology. We are talking about well-understood interactions between light and matter, governed by the trusted laws of electromagnetism and gravity. To alter the predicted TE correlation, you would need to tamper with the fundamental conditions of that primordial plasma. Perhaps the density of ordinary matter was slightly different. Maybe the timing of recombination, when atoms first formed and the fog cleared, was not exactly as we have calculated. Or, more radically, it could hint at an extra source of radiation or particles influencing that plasma, something like a background of mysterious, nearly massless particles streaming through the infant universe, subtly changing how the light scattered for the final time. The stubborn nature of these TE correlation anomalies means they cannot be easily dismissed as noise. They persist in the data from multiple independent experiments. This forces a difficult choice upon cosmologists. Either there is a subtle, unaccounted for systematic error affecting all these sophisticated instruments in the same way, which seems unlikely, or our model of the universe's composition and its early thermal history is missing a crucial ingredient. It is a whisper from the final moments before the first dawn, suggesting that even the physics we consider most settled might have a twist in its tail we have yet to read. The harmony we expect from the universe's first light continues to break down in its deepest notes. Beyond the temperature map's quiet at the largest angles, the polarization itself seems to whisper at a volume far lower than our theories predict. This is the low LE power suppression, a technical name for a profound silence, when scientists measure the power or strength of the E-mode polarization patterns across the grandest scales of the sky, corresponding to the multipole moments from 2 to 10, they find a startling deficit. It is as if the universe's first chorus, when it sang in polarized light, was missing its deepest bass voices entirely. This suppression mirrors a similar, famous lack of power in the temperature spectrum at these same vast scales, the large angle correlation anomaly we discussed earlier. But finding it again in the polarization is a crucial, independent confirmation. It tells us this is not a fluke of one measurement or a quirk of how we map temperature. It is a fundamental feature imprinted on the light itself, a genuine signature from the dawn of time. The universe seems oddly muted on its largest possible canvases. Why would both the temperature and the polarization of the cosmic microwave background lack power on scales larger than about 60 degrees across the sky? One compelling line of thought points directly to the epoch of reionization, a later chapter in cosmic history, hundreds of millions of years after the cosmic microwave background was released. The first brilliant stars and galaxies ignited, flooding the universe with ultraviolet light. This energetic radiation ripped electrons away from atoms once more, reionizing the cosmos. This process created a secondary source of polarization, a new layer of directional twist imprinted on the ancient light as it passed through this newly energized fog. The standard story suggests this reionization signal should contribute significantly to the E-mode power at the very largest scales. The observed suppression could therefore mean that reionization happened differently than we think, perhaps later, or more slowly, or in a more patchy manner, failing to generate the expected large-scale polarized glow. It is a clue that the universe's first chapters of star formation might be written in a script we have not fully decoded. Yet an even more profound possibility exists. This paired suppression in both temperature and polarization might be a fossil from a time before the cosmos was even recognizable. It could be evidence of suppressed superhorizon perturbations. During inflation, space expanded faster than light. This means regions of the universe were pushed beyond each other's causal horizons, unable to communicate or smooth out their differences. Our entire observable cosmos is just one such region. The largest patterns we can see, those corresponding to the lowest multipoles, were set by quantum fluctuations that were stretched to superhorizon sizes before inflation ended. If, for some reason, the physics of inflation inherently produced fewer of these ultra-large-scale fluctuations, if the process was biased against creating the very biggest wrinkles in spacetime, then we would see exactly this kind of power deficit on our largest maps. Our universe would be, in a sense, too smooth at its birth, lacking the grandest primordial waves. The implications of this are staggering. It suggests a constraint on the very mechanism of inflation, a hint that the driving force behind the universe's explosive growth had a specific character that filtered out certain scales. Alternatively, it might indicate that our observable universe is simply a smaller, quieter patch within an incomprehensibly vaster and more varied whole. We are not seeing the full symphony of creation, only a single, surprisingly placid movement. The low LE power suppression is more than a missing data point. It is a quiet question mark etched across the sky, asking if the universe's first moments were gentler, or its later adolescence dimmer, than we have ever dared to imagine. But the universe's deepest silences are matched by unexpected noise on the smallest scales. While we search for the faint primordial curl of gravitational waves, our telescopes have picked up a different, puzzling signal. At the fine-grained level of the cosmic map, corresponding to structures less than 1/10 of a degree across, some experiments report an excess of B-mode polarization. This is not the smooth, large-scale curl from inflation. This is a crackle of small-scale twists, a power that seems stronger than our best models can account for. The primary expected source of B-modes at these high multipoles is a well-understood cosmic process called gravitational lensing. Just as a glass lens bends light, the gravitational pull of all the matter, both dark and visible, that is formed between us and the cosmic microwave background gently warps its path. This lensing can twist the simpler E-mode patterns into the more complex curl of B-modes. It is a predictable effect, a secondary imprint from the universe's later growth. Yet the data hints that the observed B-mode power at these small scales is a bit too high. The crackle is just a little too loud. This sends cosmologists on a hunt for other contributors to this fine-grained polarization static. The first and most persistent suspect is right in our own galactic neighborhood: polarized dust. Our Milky Way is filled with microscopic, needle-like grains of silicate and carbon, spinning and aligned by the galaxy's magnetic field. These grains emit light in the same frequencies we use to observe the cosmic microwave background, and that emission is polarized. This galactic foreground is not a smooth veil, it is a complex, filamentary tapestry of its own. If our models for subtracting this dusty foreground are even slightly imperfect, residual polarized emission could easily masquerade as an excess of cosmological B-modes. It is like trying to hear a whisper in a windy desert. The rustle of the sand itself can sound like the voice you seek. Another candidate is the collective glow of all the faint, dusty galaxies throughout cosmic history, known as the cosmic infrared background. This integrated light from countless stars being born and dying could also carry a polarized signature that contaminates the deepest background. But what if, after accounting for all known dust and distant galaxies, the excess remains? Then the possibilities become truly exotic. One fascinating idea involves primordial magnetic fields. These would be relics from the universe's earliest moments, vast webs of magnetism woven into the fabric of space itself. Such fields could polarize the cosmic microwave background photons as they travel across the cosmos, potentially creating a distinct B-mode signature on small scales. Another speculative source points to the dark sector. Could certain types of decaying or annihilating dark matter particles produce a faint, diffuse emission of polarized light as they interact? Or could dark matter itself, through its gravitational influence in novel ways, generate these subtle twists? The high LB mode excess is a frontier mystery. It sits at the crossroads of the known and the unknown, where the messy astrophysics of our galaxy and the entire history of star formation meets the pristine physics of the primordial universe. Pinning down its source is not just an academic exercise, it is a necessary cleanup operation. To ever confidently detect the primordial B-mode signal from inflation, we must first understand every other possible way the universe can create a curl in its oldest light. This excess, therefore, is either a frustrating obstacle in our path, or it is a signpost pointing to entirely new physics hiding in the fine print of creation. The search for hidden twists in the ancient light pushes our instruments to their absolute limits, probing for a signal that should not exist at all. This is the speculative frontier of circular polarization in the cosmic microwave background. Until now, we have discussed linear polarization, where the light waves oscillate in a specific direction, like a rope shaken up and down or side to side. Circular polarization is something else entirely. Imagine that rope being whipped in a smooth, continuous spiral. The electric field of the light rotates as it travels, tracing out a corkscrew path through space. Standard cosmology predicts exactly zero circular polarization in the primordial glow. The physics of the hot, dense plasma of the early universe simply does not produce it. Finding any trace would therefore be a direct violation of our foundational models, a clear sign of new physics imprinted on the dawn of time. So what could possibly twist that first light into a spiral? One compelling candidate comes from the shadowy realm of hypothetical particles. The action is a light, ghostly particle originally proposed to solve a deep puzzle in quantum physics. If actions exist, and if they couple to light in a specific way, they could engage in a cosmic dance with photons as they travel across the universe. Through a process called photon action conversion, a tiny fraction of the linearly polarized cosmic microwave background, photons could transform into actions as they pass through magnetic fields and then later convert back into photons. This round-trip journey could subtly alter the polarization state, injecting a faint, telltale signature of circular polarization into the signal. It would be a fossil of this mysterious interaction written across the entire sky. Another potential source is even more fundamental: parity violating physics during the epoch of inflation itself. We discussed how hints of asymmetry in B modes could point to a handedness in the early universe. Such a violation, if strong enough, could directly generate circular polarization. If the laws of physics during those first moments truly distinguished between left and right, they could have imparted a gentle spin to the very fabric of spacetime, a rotation that would get locked into the light as it was finally set free. The hunt for this signal is a monumental challenge in sensitivity. We are looking for an effect that is predicted to be billions of times fainter than the already faint linear polarization we struggle to measure. It is like trying to detect the gentle spin of a single grain of sand on a vast, windy beach by listening only to the sound of the ocean. Current and next-generation telescopes are being designed with this ultimate precision in mind. Their detectors cooled to fractions of a degree above absolute zero to silence their own internal noise, their optics crafted to minimize any spurious instrumental effects that could mimic the signal. Why would such a Herculean effort be worth it? Because any definitive detection of cosmic circular polarization would be nothing short of revolutionary. It would not merely tweak a parameter in our models, it would blow the door open. It would provide direct, incontrovertible evidence for physics operating at energy scales we can never hope to replicate on Earth, pointing unequivocally to new particles or new fundamental symmetries broken in the infant cosmos. It would tell us that the universe's first light carries a secret spin, a final, subtle twist in the tale of creation that we are only now learning how to read. The ancient light's alignment with our modern cosmos presents a paradox that defies simple chronology. Among the most perplexing findings is a curious link between the cosmic microwave background's most famous anomalies and the grand architecture of the nearby universe, the galaxies and superclusters that formed billions of years after that first light was set free. The cold spot, that vast cold desert, appears to sit in the direction of the Eridanus supervoid, a colossal bubble of relative emptiness, the axis of evil, the ghostly preferred direction, seems to point toward a staggering concentration of mass known as the Shapley supercluster, the greatest gathering of galaxies in our local cosmos. This is more than a little strange. How can a snapshot from the universe's infancy, from a time before any stars or galaxies existed, show correlations with structures that would not emerge for eons? It is as if a photograph of a newborn baby contained subtle hints of the city they would one day help to build. The question this forces upon us is profound. Is the cosmic microwave background, the relic of the primordial universe, somehow aware of structures that formed billions of years later? The most straightforward scientific answer involves a phenomenon called the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels through the evolving cosmos, it passes through the gravitational wells and hills created by matter. If those structures are still growing, the light can gain or lose a tiny bit of energy, passing through a vast supercluster, a growing hill of gravity. The light must climb out, losing energy and making that patch of sky appear slightly colder. Conversely, passing through a supervoid, an expanding valley, the light gains energy, making that region appear slightly warmer. This effect creates a specific, subtle imprint that can link the ancient light to the later large-scale structure. But here is the catch. The integrated Sachs-Wolf effect is incredibly weak. The temperature shifts it produces are minuscule, on the order of millionths of a degree. While it can explain some general statistical correlations, it struggles mightily to account for the strength and specificity of the alignments we see, particularly with extreme features like the cold spot. The suspected Eridanus supervoid, for instance, does not seem nearly vast or empty enough to create such a profound cold imprint through this mechanism alone. The numbers, once again, fall short. This gap between prediction and observation opens the door to more radical interpretations. One possibility is that we are seeing a statistical fluke of cosmic proportions, a chance alignment that has tricked us into seeing a connection where none exists. Yet the persistence of these correlations across different analyses makes that explanation feel increasingly unsatisfying. Another, more mind-bending idea is that these alignments are not a result of the later universe affecting the ancient light, but rather a hint of the opposite. Perhaps the initial conditions of the universe, the quantum seeds imprinted during inflation, were not perfectly random. They might have contained a faint, large-scale pattern, a pre-existing gradient or texture that influenced both the formation of the cosmic microwave background hotspots and, billions of years later, the gravitational collapse that formed the greatest structures in our neighborhood. In this view, the axis of evil and the Shapley supercluster are not causally connected across time. They are siblings, both born from the same primordial asymmetry written into the fabric of space at the very beginning. This would mean the universe's largest structures today are tracing a blueprint laid down in its first fleeting moments, a blueprint we can still see in the faint afterglow of creation. The implications unsettle our linear sense of cosmic history, suggesting that the future was, in a sense, written into the past on a scale we are only beginning to perceive. That faint spiral of polarized light holds a secret timetable for the universe's first dawn. The E-mode spectrum, that map of directional whispers, is not just a relic of the initial plasma. It also carries a later signature, a secondary echo from an era hundreds of millions of years after the Big Bang, when the cosmic dark ages finally ended. This is the epoch of reionization, when the first stars and galaxies ignited, flooding the universe with energetic ultraviolet light. that fierce radiation blasted apart the neutral hydrogen atoms that had filled space, stripping them of their electrons once more and creating a diffuse fog of free electrons. As the photons of the cosmic microwave background passed through this newly energized fog on their long journey to us, they scattered off these electrons one final time. This last interaction imprinted a distinct, broad bump on the large-scale E-mode polarization spectrum, a specific hum in the data that acts as a fossil record of when and how the universe was relit. By reading the shape and height of this polarization bump, cosmologists can essentially carbon date the era of the first starlight. The story this data tells, however, is not a simple one. The standard, elegant narrative suggested reionization was a relatively quick and uniform process, a cosmic sunrise that happened everywhere at roughly the same time. But the detailed E-mode polarization data from satellites like Planck hints at a more complex and drawn-out history. The signal suggests reionization may have begun earlier, progressed more slowly, and been far patchier than our best simulations predict. Imagine a vast continent emerging from an ice age. The standard model expects the ice to melt uniformly, a steady warming across the entire landscape. The polarization data, however, suggests a messier thaw. Isolated pockets of warmth and light appear first, creating scattered oases of ionized gas in a vast, dark neutral wilderness. These pockets grow and merge slowly over an extended period, with some stubborn regions of darkness holding out longer than others. This complexity forces us to rethink the nature of the universe's first light sources. Were the very first stars and galaxies fundamentally different? Perhaps the earliest stars were monstrously huge and ferociously bright, dying in spectacular supernovae that polluted their surroundings and shut down further star formation for a time, creating a stuttering, irregular reionization process. Or maybe the primary drivers were not stars at all, but the intense radiation from the first supermassive black holes at the hearts of nascent galaxies, their brilliant quasars punching ionized bubbles into the darkness with unpredictable ferocity. The tension in the data is a gift because it pushes our telescopes to look deeper. The hunt is now on for the faint, redshifted glow of those very first galaxies, to see if their numbers and properties match the extended reionization history written in the polarization. This is not just about fixing a timeline. It is about understanding the true ancestors of cosmic structure. The prolonged, patchy reionization implied by the E spectrum would have had profound consequences. It means the ultraviolet background radiation that filled the universe was uneven, which would have influenced how and where the next generation of galaxies could form, potentially leaving an imprint on the large-scale structure we see today. The polarization of the oldest light, therefore, is more than a relic of the beginning. It is a chronicle of the universe's difficult, messy adolescence, a record of its long struggle out of darkness and into the light of the modern cosmic era. This chronicle of reionization is written on a palimpsest, a document where the original text is partially erased by later writing. The true, primordial signal of the cosmic microwave background is that original text, but it has been overwritten by layers and layers of later cosmic history. The most persistent and troublesome of these overwritten layers comes not from distant epochs, but from our own home. The Milky Way galaxy is not a transparent window. It is a brilliant, chaotic foreground, and its light pollutes our view of the primordial dawn. To see the universe's first light, we must first peel away the ghost of our own galaxy. This is one of the most formidable technical challenges in all of modern cosmology. Our galaxy emits light in the same microwave frequencies we use to observe the cosmic microwave background, and that light is powerfully polarized. There are two primary culprits. First, synchrotron emission. Throughout the Milky Way, cosmic ray electrons, particles accelerated to nearly the speed of light, spiral around the galaxy's magnetic field lines. This violent dance generates a diffuse, polarized radio glow that shines brightest at lower microwave frequencies. Second, thermal dust emission. The space between stars is not empty, it is filled with microscopic grains of silicate and graphite. These tiny particles, warmed by starlight to only about 20 degrees above absolute zero, re-emit that energy in the microwave and infrared. Because these dust grains are not spherical, they are more like tiny needles or rods. They tend to align with the galactic magnetic field. As they spin, they emit light that is polarized perpendicular to their long axis, creating a second, pervasive veil of polarized foreground light. Think of trying to listen to a faint, ancient melody playing from a distant radio station. But you are sitting inside a bustling, noisy factory. The hum of the machinery and the whine of electric motors drown out the distant signal. To hear the music, you must build a filter that perfectly understands and subtracts the sound of the factory. That is what cosmologists must do with our galaxy. We map its emission across many different frequencies, from radio waves to infrared, building intricate models of how synchrotron and dust emission should look and behave. Then, we attempt to subtract this model from our all-sky maps, hoping to leave behind the pristine cosmic microwave background. The problem is, our models are imperfect. The galaxy is more complex than our equations. The magnetic field is not a simple, smooth pattern. It is tangled and filamentary. The dust grains are not all the same size or composition, and their alignment physics is not fully understood. When we perform this galactic subtraction, we are often left with unexplained residuals, patches of polarized signal that refuse to go away. These are the ghosts in the cleaned maps. They could be nothing more than the limitations of our models, pockets of galactic astrophysics we have not yet mastered, a region where the dust is slightly hotter or the magnetic field has a strange kink. But they could also be something far more significant. What if, hidden within these stubborn residuals, is a leakage of the primordial signal we so desperately seek? Or a signature of something entirely new, like the imprint of primordial magnetic fields woven into the fabric of space, which would look remarkably similar to certain types of galactic foregrounds. The terrifying and thrilling possibility is that our greatest source of noise could be disguising our greatest discovery. Every unexplained wisp in the foreground cleaned map is therefore a cosmic crossroads. It forces a critical choice. Do we invest in ever more sophisticated models of galactic dust and magnetism, treating these residuals as a problem to be solved? Or do we dare to consider that the ghost in the machine is not a ghost at all, but a whisper from the beginning of time, masquerading in the cloak of our own Milky Way? The answer will determine whether we are meticulously cleaning a window or accidentally erasing the message written on the glass. The ghost in the machine is a pattern that should not exist. Our entire standard model of the universe's birth is built on a profound statistical assumption that the quantum seeds for all structure were Gaussian. This is a technical term for a very simple idea. It means the initial fluctuations were perfectly random, like the static on an old television set or the gentle hiss of rain. In a Gaussian field, every bump and dip is independent, with no hidden correlations or preferred shapes. The hot and cold spots in the cosmic microwave background should be just that, random spots. But what if, hidden within the subtle directional twists of the polarization, we find whispers of something more? This is the controversial hunt for non-Gaussianity in polarization maps. Scientists are not just looking for hot and cold. They are searching for specific, coherent shapes imprinted on the chaos, like finding a faint but recognizable face in the static. These are deviations from pure randomness, statistical fingerprints that could only have been stamped into the fabric of reality by the physics of the very first instant. The tools for this search are incredibly sophisticated. Researchers use mathematical filters called wavelets to scan the polarization maps at different scales and orientations, looking for patterns that stand out against the Gaussian background noise. Some analyses have claimed intriguing hints of such anomalies, specific, localized features where the polarization alignment forms a strange, coherent structure that seems too organized to be chance. One type of pattern might look like a concentrated hotspot of specific polarization directions, a kind of polarized bullseye. Another might resemble a series of aligned filaments or streaks within the map, as if the brushstrokes of creation had a momentary, consistent direction. The significance of finding such a signal cannot be overstated. Standard, simple models of inflation produce almost perfectly Gaussian fluctuations. Detecting clear non-Gaussianity would immediately rule out a wide swath of those simple models. It would point us toward more complex versions of inflation, where multiple fields interacted, or where the expansion of space hit a speed bump, creating a kind of cosmic imprint in the process. Some theories even suggest these patterns could be the scars of collisions between our universe and other bubble universes in a vast multiverse, a crash so monumental it left a bruise on our sky. Yet here lies the controversy. The claimed detections are tantalizing, but they remain unconfirmed and fiercely debated. The central problem is the same one that haunts all these anomalies: distinguishing signal from noise in an incredibly messy dataset. The polarization maps are contaminated by foregrounds, by lensing, and by the inevitable statistical noise of the instruments themselves. When you search through enough data with enough different statistical filters, you are bound to find something that looks unusual purely by chance. This is the look elsewhere effect. It is like rolling a die thousands of times. Eventually, you will get a sequence that seems meaningful 10 sixes in a row, even if the die is perfectly fair, proving that a strange wavelet pattern is truly primordial, and not just a rare fluctuation of the foreground or noise. Requires an extraordinary level of statistical confidence that has so far been elusive. The polarization data adds a crucial new layer to this decades-long search, which began with temperature maps. Polarization gives us a different, cleaner view of the same physics. A genuine non-Gaussian signature that appears in both temperature and polarization, and in the specific way they correlate, would be far harder to dismiss as an artifact. That is the new frontier. We are waiting for a pattern to speak twice, in two different languages of light, telling the same impossible story. Until it does, these strange shapes in the polarization remain cosmic maybes, the most compelling ghosts in the data, pointing toward a dawn that might have been far more textured and eventful than our smoothest stories allow. The search for a hidden twist in the cosmos leads to a force we take for granted. Among the most confounding possibilities for generating mysterious B-mode polarization is the existence of primordial magnetic fields. These would not be the magnetic fields of stars or galaxies born later in cosmic history. These would be relics from the universe's first moments, vast webs of magnetism woven directly into the fabric of space-time during its violent birth. If such fields existed, they would have left a unique, ringing signature on the polarized light of the cosmic microwave background, a specific pattern of curls and twists across multiple scales. The hunt for this signature has become one of the great, quiet challenges in cosmology, a search that tightens the noose around our theories with every new observation. Current data from the most powerful telescopes places incredibly stringent limits on the strength of any such primordial field. We can say, with high confidence, that if these fields exist, they are incredibly weak, billions of times weaker than the magnetic field holding a refrigerator magnet to your door. This might seem like a definitive no, a case closed by precision measurement, but the story is far more intriguing. These tight limits do not eliminate the idea. Instead, they transform it into a delicate puzzle. The allowed strength is so vanishingly small that it pushes the origin of these fields into the most extreme realms of theoretical physics. They could not have been generated by any ordinary process in the later, cooler universe. Their existence would demand a mechanism from the first fractions of a second, perhaps during inflation itself or in the exotic phase transitions that followed. This forces a profound question. Why would the universe go to the trouble of creating a fundamental, universe-spanning magnetic field, only to make it so incredibly faint that it barely leaves a trace? The answer might be written in the anomalies we cannot yet explain. Here is where the mystery deepens. Some of the puzzling, small-scale excesses in B-mode power that we see, the ones that don't quite match predictions from lensing or galactic dust, could potentially be reinterpreted. What if they are not mere noise or imperfect foreground subtraction? What if they are the faint, ghostly echo of these primordial magnetic fields, shining at the absolute limit of what our instruments can detect? It is a tantalizing possibility. These fields would have done more than just polarize light. In the infant universe, they would have influenced how matter clumped together, subtly altering the formation of the very first structures. They could have acted as cosmic seeds for the stronger magnetic fields we see in galaxies and clusters today, solving a long-standing mystery of how such large-scale magnetism arose. The challenge, therefore, is twofold. We must design experiments of even greater sensitivity to probe these vanishingly weak signals, pushing into a regime where the whisper of the primordial field might finally be heard above the cosmic static. Simultaneously, we must re-examine every anomaly, every stubborn speck of polarized light that refuses to fit our standard models, and ask if it holds the twisted fingerprint of a magnetic universe from its very first breath. This transforms the B-mode puzzle from a single hunt for gravitational waves into a layered detective story. Every unexpected curl in the ancient light could be a clue with multiple suspects, lensed echoes, swirling galactic dust, the signature of inflation, or the last remnant of a primeval magnetic force that shaped everything to come. The faint echo of reionization holds a number that refuses to stay still. This is the optical depth to reionization, a single, crucial parameter cosmologists call tau. It is a measure of how foggy the universe was during that second ionization, telling us what fraction of cosmic microwave background photons scattered off free electrons one last time on their journey to us. Tau is the key that unlocks the timing of the cosmic dawn. A larger tau means reionization happened earlier and was more extensive. A smaller tau means it was later and more subdued. This number is not guessed. It is measured with exquisite precision from the large-scale bump in the E-mode polarization spectrum, the very signature of that final scattering. Yet this precisely measured value has become a source of profound and persistent tension. The tau derived from the cosmic microwave background, most notably from the Planck satellite data, suggests a value around 0.054. This paints a picture of an early and relatively rapid reionization. But when astronomers look out into the universe using completely different tools, they get a different story. By studying the absorption lines in the spectra of the most distant quasars, which act as cosmic lighthouses shining through the ancient intergalactic fog, they can map when the hydrogen in deep space became transparent. These astrophysical observations suggest a later, more gradual process, corresponding to a tau value closer to 0.05. The difference seems small on paper, a discrepancy in the third decimal place. But in the high-precision world of cosmology, it is a glaring rift. It is as if you had two incredibly accurate clocks built on different principles, one claiming the sun rose at 6:17 a.m. and the other insisting it was 6:43 a.m. Both cannot be right, so where does the tension lie? Is the problem in our reading of the primordial light? The Planck measurement of tau is not direct. It is inferred through a complex statistical fit that depends on the entire cosmological model, the so-called lambda-CDM framework. Tau is tangled up with other parameters, like the density of matter and the amplitude of primordial fluctuations. If there is something subtly wrong with that underlying model, an unknown ingredient or a slight mismeasurement elsewhere, it could bias the inferred value of tau. Perhaps an unaccounted-for source of polarized foregrounds or a non-standard process in the early universe is mimicking part of the reionization signal, making it appear stronger and thus earlier than it truly was. On the other side, the quasar data comes with its own challenges. Those distant beacons are rare, and the absorption in their light only tells us about the specific, pencil-thin lines of sight we happen to have. Could the universe have reionized in a patchy manner, with some regions clearing earlier than others? If our quasar sightlines accidentally probe later clearing regions, they would give us a biased, later average for the whole cosmos. The tension forces a fundamental question about our narrative. Do we trust the afterglow of the Big Bang itself, or the fossil record written in the ancient gas between galaxies? Resolving the tau tension is not about adjusting a dial. It strikes at the coherence of our entire cosmic history. It asks whether the story we have woven, connecting the first light to the first stars, has a thread out of place. A discrepancy here means we might misunderstand the very engines of reionization, the nature of the first galaxies, or the fundamental geometry that connects their light to our instruments. Until tau finds peace, the timeline of our universe's awakening remains an open and deeply puzzling mystery. This whispering asymmetry in the cosmos may have a name and a mechanism. Among the most startling recent claims is the detection of something called cosmic birefringence. Birefringence is a property of certain crystals, like calcite, that can split a beam of light in two, rotating its polarization. The staggering proposal is that the entire universe might behave like one vast, subtle crystal for the oldest light traveling through it. The polarization angle of the cosmic microwave background, photons, appears to have rotated by a tiny but measurable amount, about 0.3 of a degree, during their 13.8 billion-year journey to us. It is as if the universe itself has a faint optical twist, a gentle hand that has turned the polarization of every primordial photon by the same minuscule amount. The potential cause for this is a ghostly interaction between light and a field permeating all of space. The prime suspect is a field associated with dark energy, or a sea of action-like particles. These hypothetical, ultralight particles could couple to photons, causing their polarization direction to slowly precess or rotate as they fly across the cosmos. This would be a direct, observable signature of physics beyond the standard model, a fundamental parity violation written in the twist of ancient light. But the mystery deepens dramatically. The most puzzling aspect of this claim is not the rotation itself, but its pattern. This cosmic birefringence appears to be anisotropic. It is not a uniform twist applied equally across the entire sky. The data suggests the rotation angle might vary from one direction to another. In some parts of the cosmos, the polarization may have twisted a bit more, in others, a bit less. This transforms a profound mystery into an almost paradoxical one. How could a fundamental property of the universe, a coupling between light and a universal field, be different in different places? It suggests the underlying cause is not a smooth, uniform background, but something textured, something with a directionality or a gradient woven into the fabric of reality. This anisotropy points away from a simple, global effect and toward a far more complex origin. Perhaps it is tied to the large-scale magnetic fields that might thread the cosmos, which could influence how the action-like particles interact with light. Or maybe it reflects an uneven distribution of the dark energy field itself, a shocking idea that would mean the force accelerating the universe's expansion is not a constant, but a variable tapestry. The implications are staggering. If confirmed, anisotropic cosmic birefringence would mean that the very vacuum of space has a hidden grain to it, a direction-dependent property that gently sculpts the oldest light in creation. It would be a final, elegant explanation for some of the handedness and asymmetry we think we see, revealing a universe that is not just lopsided in its structure, but in its most fundamental laws. These subtle twists in the oldest light are echoed in its final, fading whispers, at the very smallest scales on the cosmic map, where the hot and cold spots blur into a fine-grained texture. The universe's first light reveals the last chapter of its early story. This region is known as the silk damping tail. To understand it, picture the infant cosmos not as a clear, still pond, but as a thick, hot soup of particles and light. Photons were trapped, constantly bouncing off free electrons. In regions where matter was slightly denser, this photon pressure created a struggle. The photons fought against gravity's pull, trying to smooth out the clumps. Before the universe became transparent, these trapped photons managed to diffuse or slowly leak out of the densest regions, dragging some of the matter with them. This process, named after physicist Joseph Silk, effectively washed out the tiniest wrinkles in the primordial fabric. It sets a limit on how small a feature we can see in the cosmic microwave background. The damping tail is the precise statistical signature of this smoothing, the way the power of the fluctuations drops off at the highest multipoles, the smallest angular scales. It is a direct probe of the density and composition of that primordial plasma in its final moments. And here, in these exquisite fine details, our predictions and observations show a subtle but persistent mismatch. The data from high-resolution experiments like the Atacama Cosmology Telescope and the South Pole Telescope reveals anomalies in how this damping tail appears in both temperature and, more tellingly, in polarization. The observed drop-off in power is not quite as steep as our standard model of the plasma physics says it should be. It is as if the primordial soup was slightly thinner, or the photons diffused through it a little less efficiently, leaving the smallest wrinkles a bit more pronounced than expected. This is not a glaring error, but a quiet, systematic drift between theory and data. The implications are profound, because the physics of the damping tail depends on some of the most fundamental numbers in nature. The rate at which photons diffused relied on the density of ordinary matter, the cross-section of their interaction with electrons, and the background density of relativistic particles like neutrinos that filled the universe. A discrepancy here forces us to ask which of these bedrock ingredients might be slightly off. Could it point to variations in the fundamental constants themselves? The silk damping scale is exquisitely sensitive to the fine structure constant, which governs the strength of electromagnetism, and the proton-to-electron mass ratio. If either of these constants had a slightly different value in the early universe, it would alter how tightly photons coupled to matter, changing the damping tail we observe. While the idea of constants varying over cosmic time seems radical, it is a serious line of inquiry to explain this subtle anomaly. More likely, perhaps, is a clue hidden in the ghostly particles streaming through that plasma. Neutrinos, nearly massless and weakly interacting, made up a significant portion of the early universe's energy density. Their presence and properties affected how fast sound waves could travel through the primordial soup, which in turn set the silk damping scale. The damping tail anomalies could be whispering that neutrinos are not exactly as we have modeled them. Perhaps they interacted with each other or with dark matter in non-standard ways, or maybe their energy distribution was different. Some models even suggest the existence of an additional, sterile neutrino species that was present in the early universe, subtly altering the fluid dynamics of that first moment. This fine-grained mismatch is a testament to how far precision cosmology has come. We are no longer just looking at the broad brushstrokes of creation. We are analyzing the individual pixels and finding that their color is off by a shade. Whether the cause is a shift in nature's constants or a new property of its most elusive particles, the damping tail anomaly suggests that even the final moments of the universe's fiery birth hold secrets we have yet to decode. The fine-grained details of the ancient light are being stretched and twisted by the weight of the entire cosmos. This leads us to a powerful, cross-referenced mystery, where two different windows into the universe's structure are held up to each other, revealing a potential crack in our understanding. Scientists compare maps of the cosmic microwave background polarization with maps of cosmic shear, the subtle warping of light from billions of distant galaxies caused by the gravitational pull of all the dark matter and ordinary matter in between. This is not just a comparison, it is a deep, statistical handshake across time, probing the invisible scaffolding of the cosmos and the force that now governs its expansion. Think of the universe's structure as a vast, growing web. The cosmic microwave background polarization, especially the lensing-induced B modes, gives us a fossilized imprint of that web's earliest potential, its blueprint. Cosmic shear, on the other hand, shows us the web as it exists today, after billions of years of gravitational growth, with its strands of galaxies and dark matter. By measuring how these two maps correlate, cosmologists can trace the entire history of how structure formed. It is like having a baby picture of a giant sequoia tree and a current photograph of the full-grown forest. By comparing them, you can deduce the rate of growth, the health of the soil, and the climate over eons. In cosmology, this cross-correlation measures the integrated growth of structure and is exquisitely sensitive to the nature of dark energy, the mysterious force accelerating the expansion of the universe. Here is where the intrigue deepens. Some of the most precise measurements of this cross-correlation show a subtle but persistent tension. The observed correlation between the lensing of the cosmic microwave background and the cosmic shear from galaxy surveys appears to be slightly weaker than what our standard model of cosmology, with its specific form of dark energy, predicts. The universe's mass web, as seen through these two independent lenses, seems to be clumping together a little less aggressively than we anticipated. This is a profound clue. The growth of cosmic structure is a titanic tug-of-war. On one side, gravity works tirelessly to pull matter together into galaxies and clusters. On the other, the accelerated expansion driven by dark energy works to pull space apart, suppressing the growth of new structure. A weaker than expected cross-correlation suggests that dark energy might be even more effective at this suppression than our simple model allows. This opens the door to electrifying possibilities. Perhaps dark energy is not a constant, unchanging force, but something that evolves over time, growing stronger and more disruptive to cosmic growth than we thought. Or, more radically, it could point to a modification of Einstein's theory of gravity itself on the largest scales. Our laws of gravity have been tested with spectacular success in our solar system and in binary pulsar systems. But the vast, invisible architecture of the cosmic web is a new laboratory. If gravity behaves differently over these immense distances and epochs, it could explain why the growth of structure, as measured by this cross-correlation, seems muted. It would mean that the force weaving the universe together is not quite the one we have in our textbooks. The beauty of this mystery lies in its method. We are not looking at one anomalous map anymore. We are holding two maps, each a masterpiece of modern observational science, up to the light. The fact that their shared story does not perfectly align is not a failure. It is a guidepost. It tells us that the bridge we have built between the universe's first light and its present-day structure, a bridge made of equations for gravity, dark matter, and dark energy, might have a stress fracture in its design. As future surveys map cosmic shear with even greater precision, and as we clean our cosmic microwave background polarization maps to an even finer degree, this cross-correlation will become one of our most powerful tools. It will either confirm the standard cosmic recipe with finality, or it will force us to rewrite the rules of the cosmic tug-of-war that has shaped everything we see. The pristine signal from the dawn of time must pass through a gauntlet of our own making. Every telescope, no matter how advanced, is an imperfect machine looking at an imperfect sky, and its flaws leave fingerprints on the date we so desperately want to be pure. This is the persistent, maddening challenge of systematic errors, the ghost in every instrument that can mimic a cosmic discovery or hide one forever. We have built observatories of breathtaking sensitivity, cooled their detectors to within a whisper of absolute zero, and launched them above the distorting blanket of our atmosphere. Yet certain errors refuse to be fully eliminated. They are puzzles in their own right, whispering from the data long after the main mission has ended. Consider the simple, crucial act of calibration. To measure the faint polarization of the cosmic microwave background, we must know with absolute precision how our detector responds to a known signal. But what is a known signal in the depths of space? We often rely on the dipole, the pattern caused by our own motion through the cosmos, as a celestial calibration source. Yet if our model of that dipole is off by even a tiny fraction, that error propagates through every single measurement, potentially creating false asymmetries or masking real ones. The Planck satellite team spent years after the mission ended wrestling with unexplained calibration offsets between different frequencies, a subtle discord that could tilt the entire analysis. On the ground, telescopes like those at the South Pole face a different beast: beam asymmetries. The ideal telescope beam, the patch of sky it sees at any instant, should be a perfect, symmetric shape. In reality, it is often slightly elliptical or has subtle side lobes, little wings of sensitivity that pick up light from a slightly different direction. As the telescope scans the sky, these imperfect beams can smear signals, transferring power from large angular scales to smaller ones, or creating false patterns that look eerily like the cosmological signals we seek. These effects are modeled with immense supercomputer simulations, but the models are never perfect. A stubborn residual often remains, a haze of uncertainty that sets a fundamental limit on how deeply we can trust the maps. Then there is the ever-present challenge of 1/f noise, a type of instrumental noise that is not random static, but a low-frequency drift that mimics genuine, large-scale structure on the sky. It is the electronic equivalent of a slow, deep hum in the background of a recording. Distinguishing this instrumental groan from the genuine, faint whisper of the largest-scale polarization patterns is a problem that has haunted every experiment from WMAP to the latest ground-based arrays. We cross-check with multiple detectors, we spin the telescopes in complex patterns, and still, a shadow of doubt lingers over the very largest scales in our maps, the very scales where the most profound anomalies like the missing correlations appear. The most haunting possibility is that what we have labeled as systematic error is not an error at all. Could a subtle, misunderstood property of our galaxy's magnetic field or dust emission be creating a persistent pattern that we mistakenly subtract, inadvertently erasing a true cosmological signal in the process? The line between a stubborn systematic and a new discovery is terrifyingly thin. Each major experiment leaves behind a legacy of these unresolved puzzles, a catalogue of known unknowns that the next generation inherits. They are the quiet background tension in every cosmological conference, the reason every claimed detection is met with a chorus of questions about instrumental effects. This is not a failure of science, but its essential, grinding process. The universe's first light is a whisper, and to hear it, we must first learn, with painful precision, the sound of our own breathing. The universe's most profound errors might be the footprints of its deepest truths. Among the theoretical shadows cast across our maps, none are more elegant or elusive than cosmic strings. These are not strings in any tangible sense, but hypothetical cracks in the fabric of reality itself, infinitely thin defects of energy left over from the universe's first, violent phase transitions. Picture the early cosmos cooling from an unimaginable, unified state, like water freezing into ice. As it cools, the underlying fields that govern reality settle into new, stable configurations. But just as ice forms with cracks and fissures, the cosmos might have frozen with one-dimensional scars, cosmic strings, a single string, thinner than a proton, but with the mass of a mountain range per inch, would stretch across the observable universe, vibrating at near light speed. Its gravitational influence would be immense, and it is this gravity that would carve a unique, razor-sharp signature into the polarized light of the cosmic microwave background. As this ancient light passes by a cosmic string, the severe warping of spacetime around it would create a step-like discontinuity in both the temperature and the polarization maps. It would not be a blurry smudge or a diffuse glow. It would be a clean, sharp edge, a line across the sky where the temperature and the polarization angle jump abruptly from one value to another. Think of looking at a perfectly smooth, patterned wallpaper and discovering a single, straight seam where the pattern is offset, a clear line where the whole design shifts. That is the kind of precise, geometric anomaly a cosmic string would produce. This theoretical clarity makes the search for them so compelling. Scientists have scanned the exquisite maps from Planck and other observatories, using sophisticated algorithms to hunt for these telltale edges or line-like features in the polarization data. And they have found candidates. There are unexplained, filamentary features and curious alignments of point sources that resist explanation by known astrophysics. Some of the most discussed anomalies, like certain cold spots or specific linear patterns, have been put forward as tentative, controversial evidence. One such feature, a strange linear arrangement of points in the polarization data, was even dubbed a potential string candidate by researchers, though it remains far from confirmed. The controversy is intense because the stakes are cosmic. Confirming a single cosmic string would be a discovery of Nobel Prize magnitude. It would provide direct, observational proof for grand unified theories of particle physics, offering a glimpse into energies a trillion times beyond what our largest colliders can reach. It would be a relic from a time when all the forces of nature were one, yet the evidence remains stubbornly ambiguous. The suspected features could be statistical flukes, chance alignments of noise, or the smeared signatures of more mundane things like the filamentary structure of our own galaxy's magnetic dust. The polarization data is key because the specific, predicted jump in polarization angle across a string's path is a much cleaner signature than a temperature step alone. Finding that paired signature, the temperature and polarization edge in perfect, linear alignment, is the holy grail, so the hunt refines itself. New telescopes are designed with ever-sharper vision, capable of resolving finer details to spot these cosmic cracks. The search is a beautiful paradox. We are using the most advanced technology of our age to look for the frozen imperfections of the universe's birth, hoping to find a flaw in the ancient ice that proves our most elegant theories of its fiery origin. The most speculative answer to these cosmic flaws lies beyond the edge of everything we know. If our universe is not alone, but one bubble in an infinite, frothing sea of creation, could we see the bruises from a collision with a neighboring reality? This is the ultimate frontier of cosmic microwave background anomalies, where unexplained patterns become potential imprints of the multiverse. The idea emerges from theories of eternal inflation, which suggest our universe underwent its rapid expansion within a much larger, ever-inflating meta-universe. In this picture, new bubble universes are constantly budding off, expanding into the endless void. Occasionally, these bubbles might collide. The impact of such a collision, a cosmic car crash of unimaginable scale, would send a shockwave rippling through the infant universe, leaving a distinct, circular scar on the fabric of spacetime. As the cosmic microwave background radiation was released, that scar would be frozen into the map of the sky, appearing as a nearly perfect, circular feature with a specific temperature and polarization signature inside its boundary. It would be a bullseye from another reality. Scientists have, in fact, scoured the data for such features. Several years ago, a team claimed to have found 4 unusual, large circular patterns in the WMAP satellite data that were cooler than their surroundings, which they controversially suggested could be candidate collision imprints. The polarization data adds a critical new layer to this search. A genuine bubble collision would not just create a temperature ring, it would also generate a specific, predictable pattern of polarization within that ring, a swirling or radial alignment of the light's direction that would be extremely difficult to produce by any known astrophysical process. Finding such a paired signature, the circle and its unique polarized fingerprint, would be the closest thing to a smoking gun. Beyond collisions, the multiverse might leave subtler traces. The strange non-Gaussian patterns we discussed earlier, those coherent shapes that defy perfect randomness, could be fossils from a time before our Big Bang. If our universe was born from the decay of a prior state in the multiverse landscape, that decay process might have imprinted specific, non-random correlations into the quantum seeds of our cosmos. Certain types of these statistical anomalies, particularly ones that look like localized hot or cold spots with specific polarization properties, have been proposed as possible signatures of this complex birth. The controversy around these ideas is immense, and for good reason. The primary challenge is the same one that haunts all anomalies, but magnified to an extreme: the look elsewhere effect. When you search a map as large and complex as the cosmic microwave background for any unusual shape, you are almost guaranteed to find something that looks peculiar purely by chance. A few circular features in a sky of random noise are statistically expected. Proving one is a collision requires not just finding the circle, but matching its every property, including its polarization, to the precise predictions of a bubble collision model. So far, no feature has passed that extraordinarily high bar. Furthermore, other, more mundane explanations always exist. Could a large circular feature be the result of an unusual confluence of several smaller fluctuations? Could it be an artifact of the way we process the data to remove galactic foregrounds? The polarization data is key because it offers a way to break this deadlock. A true multiverse imprint would obey a very specific, complex set of rules linking temperature and polarization. An artifact or a fluke likely would not. This transforms the search from a hunt for strange shapes into a forensic analysis of their deepest structure. We are no longer just asking if a circle exists, we are asking if that circle tells a coherent, physical story written in the language of twisted light. While the evidence remains speculative and hotly debated, the pursuit itself reshapes our perspective. It forces us to consider that the greatest anomalies in our sky might not be errors in our theories, but messages from a reality so vast. Our universe is merely a single note in its symphony. The 25 anomalies are not a closed book, but a prologue, the most profound, unexplained feature in the cosmic microwave background might be the one we have not yet seen at all. Our current maps, for all their exquisite detail, are still limited. They are like the first grainy photographs of a distant continent, revealing coastlines and major mountains, but missing the hidden valleys, the subtle rivers, and the life that moves within them. The next generation of observatories now being built on high deserts and at the South Pole are not merely upgrades. They are leaps into a new realm of perception. The Simons Observatory and the colossal CMB-S4 project will have orders of magnitude more detectors, mapping the sky with a speed and sensitivity that dwarfs our current efforts. Their mission is clear: to hunt the whispers. They will stare down the faintest B-mode curl with such precision that they can finally confirm or rule out the inflationary gravitational wave signal, the holy grail of cosmology. They will dissect the polarization of galactic dust with forensic detail, finally separating its complex tapestry from the primordial light. They will measure the cosmic birefringence angle, if it exists, with enough certainty to declare it a law of nature or a statistical phantom. Every anomaly we have discussed, from the axis of evil to the damping tail mismatch, will be subjected to this new, merciless scrutiny. But the true purpose of such instruments is not just to solve the puzzles we already have. It is to find the puzzles we cannot yet conceive. The greatest discovery these observatories could make is a signal that does not fit any of our models, a pattern in the polarization that our current theoretical vocabulary cannot describe. It could be a correlation so bizarre it points to a pre-Big Bang universe. It could be a polarization signature that reveals dark matter not as a passive substance, but as an active participant in the forces of the early cosmos. It might be the definitive imprint of a cosmic string, or a statistical scream of non-Gaussianity so loud it forces us to abandon simple inflation forever. This is the ultimate mystery waiting in the ancient light. We are building machines to listen for a note that is not on our musical scale. When it is heard, it will not be a gentle adjustment to our cosmic story. It will be a revelation that the universe is far stranger, more complex, and more wondrous than our boldest theories have dared to suggest. The map of creation is still being drawn, and its most important feature may be the blank space marked only by a question. 25 Whispers from the Dawn of Time. We have journeyed through a map not of stars and galaxies, but of profound cosmic silence, unexpected alignments, and ghostly twists in the oldest light. These are not mere data glitches or statistical noise. Each one, from the haunting axis of evil to the speculative bruises of a multiverse collision, is a potential key. They are points of tension where our elegant story of the Big Bang meets the stubborn, whispering data, and the story bends. This polarized light is more than a relic. It is a cosmic interrogation. Every anomaly asks a fundamental question, probing whether our assumptions about isotropy, inflation, and even the constancy of nature's laws are complete. The cold silence at the largest angles, the lopsided power of the hemispheres, the stubborn curl that hints at a universe with a handedness, these are not problems to be solved away. They are clues to be followed, perhaps into a deeper, stranger truth. To study this light is to stand at the edge of human understanding, confronting the limits of our knowledge with humility and awe. The greatest discoveries in science have always emerged from such places, from the tiny discrepancies in Mercury's orbit that led to general relativity, to the unexpected faintness of distant supernova that revealed dark energy. The 25 unexplained features in the cosmic microwave background polarization are our generation's discrepancies. They tell us that the universe's first chapter, written in polarized light, contains sentences we are only now learning to read, and some we cannot yet decipher. So as we look up, we are not just looking back in time, we are looking into a mirror that reflects the boundaries of our own comprehension. The true nature of reality may be encoded not in what we have already explained, but in what still, beautifully, remains unexplained. Which of these 25 cosmic puzzles captures your imagination the most? Is it the great cold spot, the coordinated dark flow, or the potential spin of cosmic birefringence? Let us know in the comments below, and subscribe to continue this journey into the deepest mysteries of our cosmos.